Good morning, good afternoon, or good evening. We are now on question 3 of the Step 3 2024 paper. As with all these videos, you should have had a go at the question first and either completed it successfully and are looking for other ways to think about the problems, or have had a strong attempt and now have got stuck and are looking for hints. As always, once you get a hint, I'd heavily suggest pausing the video, having a go with that hint yourself, seeing how far it will take you before coming back and watching the rest of the video. As soon as you do watch someone else's solution, you lose a lot of value of the problem solving process. So here we are in question 3 on the Step 2024 Step 3 paper. So here we have a function defined, a g of x is defined as a ln and a fraction. And we're subtracting off the fraction. It might be worth considering what might this function do? How might it behave? Things to be to observe is we have a 1 over x, so x being 0 is a really bad idea. However, the question has restricted to x being positive. We also could have had the situation where this whole thing in here was negative, but again, prevented by the fact that x is positive. And again, the two issues here of being 0 and minus 1 are non-issues in the domain that we are considering. We also have the condition that this c value is greater or equal to 0. That's surely going to come in later on. And if we look at part A and B, we're trying to show it has a positive gradient when c is bigger than a half. And we want to know when it has a negative gradient for the remaining regions for c. So if we're talking about positive gradients, then we need the gradient itself. So we need the derivative of this function, and that means we need to differentiate ln, which is, well, ln differentiates to 1 over. Chain rule says we put the derivative of the top, the derivative of the argument on the top, which is negative 1 over x squared, minus, now this next one we probably need to product rule, and if you want to do the product rule by setting the u and the v, do it. If you're happy to do it a little bit quicker, then fine, as long as you are accurate. So product rule says differentiate the top times by the denominator minus differentiate the denominator times by the top. Derivative of the denominator would have been 2x plus 1 all over the denominator squared. Okay. How much do I want to clean up before I just go for it? I probably want to do some amount of cleanup here. The first fraction I'm going to times top and bottom by x squared. That's going to be negative 1 over x squared plus x. This clears all the fractions inside the fractions, minus. I'm not going to touch the denominator for now, but I am going to deal with the numerator. Numerator is saying we've got an x squared minus 2x squared, so I've got a minus x squared. I've got a plus x plus 2c, well, minus 2cx minus x, so those x terms cancel, and we leave a minus 2cx minus c. And how exactly do I want to simplify this? Because remember, we're aiming to show that this is a positive gradient for all x. There are some things which are really good already. This minus sign here would make each of these pluses, and each of these terms individually, as c is positive and x is positive, are positive. Issue is that this term is a subtract, so could potentially make it negative overall. So I do think we need to smash these two fractions together. So we're going to have a single denominator of x plus 1 squared. And notice in the denominator here is just x plus 1. So that's going to become a negative x plus 1. And I'm going to deal with each of these negative signs on the other fraction. And then another simplify step. Let's have a look what has cancelled this time. We've got a negative x squared. So we're going to be left with no x squared term. And we're going to have a minus x to go with my 2c. Now that should be really pleasing, because that's exactly the condition of c being a half. If c is bigger than a half, then this bracket here is greater than 0. So let's put that in. So this is greater than, could it be equal to 0? Yes, if c was equal to a half, well, no, actually, if c was equal to a half, this thing would be 0, but this thing would be positive. And as c gets, well, I suppose x could be, well, x still has to be positive, and c is positive. Yes, this is going to be a strict inequality. It's strictly greater than 0 when 2c minus 1 is greater than or equals to 0, i.e. c is greater than or equal to a half, as c is greater than 0, x is greater than 0. So as we already have the x and c being positive, we can just look at the coefficient of the x and put a condition on that. So let's actually answer the question. Thus, g of x is increasing when c is greater than or equal to a half. Nice. Okay, so now we want to consider, this was part A, we now want to consider the case when 0 is between, c is between 0 and a half. And then we want to find out when that has a negative gradient. So one thing to notice is the denominator here is a squared, so it's always positive. So we can say g of x has negative gradient precisely when 2c minus 1x plus c is less than 0. So when this thing is negative, then I have the negative gradient. Well, that is saying that x, and we need to be a little bit careful here. So I am going to do it in 2 steps, because straight away this looks quite bad because it's saying x is less than a negative number, but in the region, this thing here is negative. So that's when x is greater than negative c over 2c minus 1, which I'm just going to swap the signs, as 2c minus 1 is negative in 0 to c to a half. So we have a negative gradient when c is bigger than this c over 1 minus 2c. And there's no problem with the denominator because we can't actually equal a half, which would have made this a divide by 0, which would have been bad. Okay, find the values of x for which that has a negative gradient. It is those values of x. Nice. Moving to part 2 of the question. It is given that for all c, g of x is going to go to negative infinity as x goes to 0. So it's telling us the asymptotic behavior when x goes towards 0. Sketch for x positive the graphs in those cases. So in part A, we have c being 3/4, which means from I part A, g of x has positive gradient. So g of x is going to be increasing at all times. So it Well, we know when x is close to 0, g of x is close to negative infinity. So we've got the y-axis here being an asymptote. It's always going to have a positive gradient. And if we do consider briefly what happens when x goes to infinity, so as x goes to infinity, I'm going to do that slightly further over here, g of x, well, ln of 1 plus 1 over a huge is going to look very much like ln 1, which looks like 0. And the other term is linear over quadratic. The quadratic on the denominator wins, so that's also going to look like 0. So g of x is also going to tend towards 0. So we have the positive x-axis also being an asymptote. So you've got the y-axis being an asymptote and x-axis being an asymptote, a positive gradient always, which in particular means there is no stationary points. So the only way for that graph to do those couple of things is just to be that branch down there with the asymptotes. And I'll actually put that slightly clearer here. The x-axis is an asymptote. It looks like in the picture, but let's be very clear for the examiner. Okay, quite a boring graph for how much algebra went into it, but that appears to be the correct graph. Now part B is going to be a little bit more complicated. So part B, we've got C being a quarter. Now from the previous part of the question, that says we are decreasing for x greater than a quarter over 1 minus 2 lots of a quarter. Well, the denominator there is 1 minus a half is a half, so that comes out overall as a half. Could just times top and bottom by 4, and we get exactly the same result. So we're decreasing when x is greater than a half, increasing for x less than a half, which tells me we have a stationary point at x equals a half. I kind of want to know what the y value is. More than anything else, know whether it's a positive or a negative. So this is going to be ln 3 minus, now this is a half plus a quarter over a half times 1 plus a half. Maybe the easiest way, collect like terms on the top, collect like terms. Okay, so it's just 1. So ln 3 minus 1. Now the slightly interesting thing, ln 3 is slightly bigger than ln e. E is slightly less than 3. So ln 3 is slightly bigger than 1. So this thing is positive. So, and if I let x go to infinity again, it's still going to have the x-axis asymptote as x goes to infinity. G of x goes to 0. So you've got a lot of the same features, except now we have a stationary point. So we still have to have our y-axis being an asymptote. But now we have our increasing region up to a half, our decreasing region bigger than a half. We're not going to get another stationary point because we're decreasing for the entirety of this time. So there's no increasing section to make that stationary point. So we're actually tending to the x-axis from above this time. And I'm also going to label on this being ln 3 minus 1. This is y equals g of x. And I probably should go and try and find that point. Now I have gone to find the stationary point, so that's maybe good enough. I'm going to have a quick think if I can find that easily. We're talking about ln 1 plus 1 over x being now equal to x plus a quarter, x plus 1. I'm feeling not great about solving this equation. To get rid of the ln, that's going to be e to the power of all of that stuff. And I'm mixing algebra and exponentials. Those equations typically don't have a nice exact solution. You have to do some kind of numerical methods on that. So not worth doing. But that is my graph. Rereading part 2, just check I haven't done anything silly. For all C, we have a y-axis negative asymptote sketch in the cases. Lovely. So that's part I and double I done. And now we're moving on to part 3, where we've been introduced to a new function. So we've got a new f of x, which is 1 plus 1 over x to the power of x plus c. One should probably first consider how this is linked to part I, and certainly if I take ln of this function, I'm getting something that could almost, as in it's got the ln of 1 plus 1 over x, that's almost something that we could link to part I. Not directly though. So let's see if we can do this. Maybe we can link some of the ideas that we had with the g with this f. We are now trying to show, again, just for x positive, that f is decreasing when c is bigger than a half. Okay, well that was backwards from what g was. G was increasing in that region. F has a turning point between when c is between those points, and f is increasing when c is 0. So 3 different-ish skills, all of which unfortunately require the derivative of this f. So we need to somehow work out how to differentiate f. And if you've seen this kind of function before, the trick is to write it as e to the power of ln of the thing, and that allows you to bring the power down in front of the ln, still up in the power of e. So I'm going to rewrite f of x in that slightly silly way, and then I want to differentiate this, which involves differentiating the this power using the product rule. So if I differentiate that, I'm going to have an x plus c times the derivative of the ln term. And we have already done that once. That gave us a 1 over x squared, negative 1 over x squared on the numerator, plus the ln term times the derivative. So that's plus ln of 1 plus, all multiplied by the e to the power, which I'm going to put back as the that as so. How much again do I want to clean up? I probably should clean up entirely. I'm going to put the ln term first because the second term is a minus, times in top and bottom by x squared. I'm left with x plus c, and the denominator, one of the x's gets used and the other x can just sit there. And you may now, I hope you can now see how part I and double I are coming in this question, because this big bracket here is exactly g of x. So the derivative involves g of x as a coefficient. Okay, so now we would like to show whether or what the behavior of f is. So for part A of this section, c is greater than or equal to a half, which means, and if we look back, this is from part 2, well, it's kind of from part 2, part A, but that was only a special case. So this is going to mean, well, the g of x is positive gradient, but we know it started negative and it has an asymptote. So in that case, the g of x was less than 0 for all x. And then also notice that this thing is always greater. It's always greater than 1 to a power. So this is always greater than 0, which means that f dashed of x, which equals g of x, 1 plus 1 over x to the x plus c, is always less than 0. I've got a negative thing times a positive thing, as 1 plus 1 over x, x plus c is greater than 0 for all x, i.e. f is decreasing for x greater than 0. Nice. Part B. So now we're in the case where we're between 0 and a half, and it's put strict inequalities on both of these. Now we want to show that f has a turning point. Well, this is saying, if we look back to the g, g is, and it's talking about increasing and decreasing. Now I kind of need to be worried about where this stationary point here is, because I'd quite like to say that at some point g of x is 0. If I can say at some point that this term here is 0, then that gives me a point where f dashed of x is 0, i.e. there's a stationary point for f. So if I look back, and it does from this picture, we do have a 0 here, but this was quite a special, this was a special situation for a special value of c, not a general value of c. So I can say that there's a stationary point, and the stationary point will happen at this crossover. But g having a stationary point, we then need to show that this stationary point has a positive g of x value, because then we can say we started negative, we got to somewhere positive, so somewhere in between had to be 0. That seems like a lot of effort, because this thing, I don't really want to sub into g, but I might need to. And even if I sub it into g, does it automatically mean that g comes out to be positive? It feels like it should. We've kind of got, if we take this kind of shape to its extreme, it gets closer and closer, then eventually it'll pop above and come down. That feels quite natural for this kind of function. So let's have a go. So between those values, g has, oops, I was trying to undo something which happened too long ago. G has a stationary point at x equals c over 1 minus 2c. And I really want this to be positive. Now, when I showed it was positive with the particular situation of c being a quarter, I could use the fact that ln 3 was less than 1 to compare these values. Maybe something similar will happen. Feels a little unlikely. Trying to think if there's a better way, but it's got to the point now where I feel like I just have to do it. So let's try and do g of this thing, which is going to be ln of 1 plus 1 over it, 1 minus 2c over c, minus, and this is the term which I really didn't like the look of, c over 1 minus 2c plus 1. So that term, I think I want to times top and bottom. Now really I need to times by 1 minus 2c squared, because there's 2 sets of it in the denominator. 1 minus 2c squared. Let's hope that simplifies nicely. The ln term at the front, if I smash that into a single bracket, I'm going to have c over c. So that's 1 minus c, which I might even turn into a 1 over c minus 1 later. I'll leave that on the next line as I might want to do this. I don't know yet. And on the numerator, we're going to have c lots of 1 minus 2c plus c times that thing squared. I'm going to expand that out because I'm probably going to need that expanded out later. Over denominator, I've got a c, and the other cancels the thing in the bracket, c plus 1 minus 2c. So that's going to be just a 1 minus c. So let's simplify. I've got a 4. Oh, no, there's a common c that I can cancel out. So let's cancel those c's out. That's going to make it slightly easier. We're going to have a 4c squared minus 6c. Have I swapped a sign somewhere? No, I haven't, not yet. I'm not liking the fact that I've got this minus 6c on the inside with a minus on the outside as well. Now I wanted to show that this was positive, which it's not looking particularly positive right now. And it's not looking like there's an easy way to show it's positive without doing a lot more work. Now we have been told to show those as station points, so this thing does have to be positive. Let's do a quick little check of algebra, make sure I haven't done anything too silly with any of my expansions. Okay, now this is definitely the awkward bit. We do know, and we do need to remember, that c is between 0 and 1/2. However, which does mean that this term here is positive. 1 over one of those values will certainly be bigger than 2. So this is ln of something bigger than 1. So that thing is certainly positive. So if I can show that this here is certainly negative, then I might be in a good spot. And normally the best bet when you are faced with equations like this is to complete the square. So I'm going to leave, now I could leave it in that form. I'm not sure which of these forms is more obvious, but I think it's probably slightly more obvious that this is positive. Now, do I want to swap some signs? No, let's try and complete the square. So I'm going to say 2c, which will give me the 4c squared. 2c times something doubled, minus 3 over 2. So that's a boundary point of 3/4. So that will give me my minus 6c. That's got plus 9 over 4. So it's going to be minus 1/4 to get back to the 2 over 1 minus c. Now, is this thing always negative? Well, I'm only allowed to be between 0 and c. 0 and 1/2. So if I sub 0 into this, this is certainly positive. If I was to sub 1/2 into this, it's still certainly negative, which is what I wanted. So this thing here is going to be bigger than ln of 1 over 1/2 minus 1, which is bigger than ln 1, which is 0. So that thing's always positive. This thing here, and this is because the stationary point, when c, this That's when C is a quarter though, which is within my range. So let's think about this quadratic. It is a, I'm ignoring the minus sign in front. So it's a positive quadratic. The denominator is just positive, so I don't need to worry about that. It's a positive quadratic. It has a minimum point at negative a quarter, and it obtains that when C is 3/4. So we need to know the solutions of this quadratic. So it'll equal, when I rearrange and square root, 2C minus 3/2 would be plus or minus a half. If it's positive a half, that's when C is 2. When it's negative a half, that'll become 1, that's a half. Is that coming out to be positive? Between 0 and a half, are those my solutions? Let me just check. So if I were to sub a half in here, that's 1 minus 3/2, that's negative a half squared. That does give a solution. Because it's this part of the graph here that I care about, and it's positive there, and I didn't want it really to be positive there. Because I want this whole thing to be positive, so I quite like this fraction to be negative. So I'm subtracting the negative to make it more positive. Otherwise, my kind of heavy-handed approximations on this side aren't sufficient. I certainly have that. It's certainly a positive quadratic. 1 minus C is certainly positive. Now I could try and work out what this point here is, and therefore put some better bounds on, but those bounds are going to depend on C, whereas that point does not depend on C. So that's when C is 0. So that's, if I go back up to this version of it, that's going to be the point 2. But then when C is 0 over here, we're shooting off to infinity, basically. Which is awkward, so this thing is positive in 0 to C to a half. Not what I wanted. Because now I need to be a lot more careful with the way I bound the other section. So this other part, let's think more carefully. Unless, so there's another way to show that this stationary point is positive, and that's taking from the other part of this picture, and it's the fact that we're coming from this stationary point from above. So if we can show for really big x values that the g function is positive, we only really need the g function to be positive at any point. If g is positive at any point, well, it started being negative, there are no breaks in positive when x is positive. So an alternative is just to pick any value to sub into this g to show it's positive. So maybe that's a smarter approach rather than trying to sub in this very special stationary point value. Well, it has to be bigger than whatever this is. Well, it doesn't have to be bigger, but it'll make sense for it to be bigger than that. If I sub in, is this ever bigger than 1? If I say C over is greater than 1, 1 minus 2C is positive in this region. So that'll be 3C is greater than 1, and C is greater than a third. So that's a possibility. If I say greater than 2, that's going to be 5C is greater than 2/5. Now it feels like this stationary point can be as far along as it likes. If I just put an N here, that will be C would be greater than N over 2N plus 1. And this thing is always slightly smaller than a half. So I can always get, the point of that is I can always, no matter what integer, or any value, I could have pushed the stationary point further beyond that value. Okay, I spent a long time thinking about this section, so in such an exam, I know it has to be the case, so I'll put a little note to the examiner and leave a bit of space to potentially come back later. So required to show G of this thing over 1 minus 2C is greater than 0, then G goes from negative in the limit x goes to 0 to positive at stationary point, which means that G of something equals 0 for some y positive. I'm basically using the idea of change of sign. I've gone from negative to positive, so there is a solution somewhere in the range, which would mean that f dashed at y would be 0 times the thing that can't be, which is the thing that's always positive up here, i.e. f has a stationary point. To show that G at that value is positive, we got a bit stuck on. I'll probably go back and have a look at that after I finish recording this video. I'll leave some space around here and I'll fill in the working after. Part C of the question, show that f is an increasing function when c is 0. So when c equals 0, f dashed of x is, let's pull that from the previous section, is going to be ln of 1 plus 1 over x plus x over x plus 1, which is just the g again, but the g now we see is 0, 1 plus 1 over x to the power of x. So we want to show that this thing now is always positive. So, well, again, this thing over here is always greater than 0. That's something bigger than 1 raised to a positive power. So we want to think about this thing here, which is the g of x, when c is 0. So when c is 0, how does this g of x behave? G of x has a stationary point, or even better, we can say g of x is decreasing from is decreasing, and this is now I part B. What did it say? It's decreasing. I part B said for x bigger than this value, but when c is 0, that's for all x greater than 0. G of x is decreasing by that for x greater than 0 with a stationary point at x equals 0 only. It's decreasing for that whole region, and we've been told, or we've worked out repeatedly, and g of x tends to 0 as x tends to infinity. So really all we need to show is that g of x starts being positive. And that is a little bit difficult because we were given the fact that for all c greater than 0, oh, I got a sign error when I copied that over. It's a minus there. We were told that when c was positive, g started being at the negative asymptote. So why, when c is 0, did it suddenly swap over? And that's not necessarily obvious, except I can write that g of x thing, it cancels slightly. So g of x equals ln of 1 plus 1 over x minus 1 over x plus 1. The x's there cancel, which is probably the reason why things have swapped over. We now have 1 over linear rather than over quadratic. So when x goes to 0, what does this do? Well, we know ln of 0 goes to infinity. We know this thing here looks like it's going towards 1. So really we want to know which of these two terms is bigger as we get close to 0. We could sub some numbers in, but that's always a bit awkward. I was thinking briefly whether I want to sub in a sequence like 1 over n and look at convergence in a clever way. Because that could potentially work. I'm also thinking I could do a Maclaurin style expansion on this. However, when x is going to 0, these terms are actually going to infinity, so 1 over that squared, 1 over that cubed cannot just be ignored. I could split this into ln of x plus 1 minus ln x. And then my Maclaurin expansion on this would just work. Really, I want to show, I'm trying to show that the g of x graph looks like this. Now, could I just sub in a small, if I just sub in any value and show that any value comes out to be positive? If I show maybe this point here comes out as positive, is that enough? I think it is actually, because then we have a graph that has a maximum, it has a positive value and it's tending towards the negative infinity. Well, it can't start down here, have a maximum, and still go up there with having with being only decreasing. So actually it's just a feature of the setup. If you're decreasing and you're tending towards 0, then you had to be positive. So this implies that g of x is greater than 0 for x greater than 0, which means that this f dashed of x is greater than 0 for x greater than 0, i.e. f dashed of x, or say just f of x, is increasing. Yeah, so when that stationary point moved all the way onto the y-axis, g of x did something extra weird. In every other point, g of x had the asymptote down at the negative y-axis, but as you move that stationary point closer and closer to the y-axis, this very special point where it hit the y-axis did something a bit different. And you could probably say a lot more about it, about exactly how this stationary point is behaving. Finding exactly what the y value of that stationary point is not an easy activity, because you're taking that limit. These functions are not defined when x is 0. So you need to take limits to worry about what's actually going on. A little disappointed I didn't manage to clean out part 3, part B, dealing with that. And if you do have a better suggestion, please do let me know on how to either show that that stationary point of g is positive, or to show that g has a root. Please do let me know, because that will annoy me for a while. And keep looking at the rest of the playlist. I'll have all the other questions from this paper hopefully equally useful to you.